Welcome to problem solving session for the course Linear Algebra. I'm Siddhi Balu Ambore from IIT Gandhinagar, and today we will discuss problems related to syllabus from week 12. That is problems related to orientations, determinants, and volumes. So let us start with our first question. So let A be Aij in MnK. So this K is filled. And for I hope you know what this MnK means. I will recall it. For for C1, C2, Cn in K star. So this K cross means non-zero. So this K star means K minus just this zero since K is a field. So in general, this okay, I will tell that later on. So we have to prove that determinant of Aij, that is this matrix A, is equal to determinant of this Ci Cj inverse Aij. And in particular, uh, determinant of Aij is equal to determinant of minus 1 power I plus j Aij. This is what we need to prove. So what I was saying that this K is a field. So this K star, that is K minus 0, is a set of all invertible elements in K. And this is also known as set of all units in K. So since K is a field, every non-zero element in K is invertible. But in general, if R is a ring, then this R star in general denotes the set of all units in R. So that's just notation which I wanted to point out. So yeah, so we have this A matrix, MnK, in MnK. So that is n cross n matrix where entries are from K. K is a field, and C1, C2, Cn are non-zero elements from K. That is, they are units and invertible in K. And we have to prove that this is determinant of Aij is equal to determinant of Ci Cj inverse. And yeah. So how this matrix actually look like? Suppose so A is this Aij, and let us call this matrix this one as B. Let B be this Ci Cj inverse Aij. So entries are of this form. This C1 inverse A11. This is C1, C2 inverse A12, and so on. And here also it is C2 C1 inverse A21. And the entries go like this. Here it will be Cn inverse ANN. Okay, so the matrix looks like this, and we have to prove that the determinant of this new matrix is actually equal to determinant of A. So how to do this? So there are various ways you can calculate this, but the easiest way is to understanding this. So we define this matrix. So we have this C1 to Cn are in K star given. Okay, and so we define this matrix D as a diagonal C1 to Cn. So this is actually this matrix C1, C2, Cn, uh, in the diagonal, rest all entries are 0. This is my matrix D. Okay, so we'll see what this B does when I multiply it with matrix A. So let us do it with 2 cross 2. So suppose A is my this matrix A11, A12, A21, A22, and my D is suppose n is 2, just to understand. And D is this matrix C1, 0, 0, and C2. So what this DA does to my matrix, and A is this A11, A12, A21, A22. And then this will give me this C1, A1, yeah, C1, A11 and 0. Then C1, A12 plus 0. Then next is C2, A21, and then I get C2, A22. So this is what it is doing is it is multiplying the the first entry, this first diagonal entry to my first row. So everything in diagonal. And if you see, so what it is doing is, so if my D is, so DA in general is this matrix CIAIJ. Okay, this is what. And so what now I do, and the next I want it, so we got hold of this thing. We got hold of this CI and AIJ. Okay, and now I want CJ inverse. So what I will do is I will define this new matrix E. This is again a diagonal matrix of C1 inverse, C2 inverse, and Cn inverse. So this is of this form: C1 inverse, C2 inverse, and Cn inverse. Uh, in diagonal, rest all entries are 0. Okay, and yes, and now I will check what this does. This A into E, multiplying A and E. So let us again take n to be 2. Then my A will be, AE will be this A11, A12, A21, A22, and multiplied with this C1 inverse 0, 0, C2 inverse. Okay, and then what this will do is A11. So let me write the constants. A C1 inverse A11, then C2 inverse A12, again C1 inverse A21, and C2 inverse A22. So what this is doing is, in general, this AE is, in general, this AE is CJ inverse AIJ. Okay, so now I have hold of this thing. Okay, so this B, this matrix B, if you check, this B is nothing but DAE. Okay, you can check this, and or we can do this for 2 cross 2 matrix now. So, so for example, if n is equal to, so hence we get B is equal to this DAE. Okay, the sequence of multiplication is important. So and then yeah, so what? So yeah, let us check for n is equal to 2. So DAE is C1 0 0 C2, A11 A12 A21 A22, and C1 inverse 0 C2 inverse. And if you check, it will be, let us do this first. I mean, it won't change anything because we have already calculated this. What it does is, it is doing C1 inverse. It is the same matrix here. C1 inverse A11, C2 inverse A12, C1 inverse A21, and C2 inverse A22. So what it does is it multiplies the first diagonal entry to the column. And what this matrix does is it multiplies the diagonal entries to that corresponding, for example, ith diagonal entry to ith row. So here also it will the same thing will happen, and I will get C11, C1, C1 inverse A11, C1, C2 inverse A12, C1, yeah, this will be, this is C2, yeah, this is A2. So this is C2, C1 inverse A21, and C22, sorry, C2, this is C2 inverse A22. And this is what my matrix B as we wanted. Okay, so I get that. Hence, you can just simply understand this. Okay, when I multiply by a diagonal to a matrix, pre-multiply and post-multiply by matrix. When I pre-multiply by diagonal matrix, each ith diagonal entry gets multiplied to the ith row. And when I post-multiply by any diagonal matrix to my square matrix, each ith entry get multiplied to the ith column. That's like known fact. I mean, you can multiply and see it. So what we did is we just tried to express this B matrix, which is asked. So we are asked to find the determinant of this matrix, Ci, Cj inverse Aij. I hope I'm audible. Let me just check. Hello.
Hello.
Yeah. So yeah. So what I was saying is that we have to calculate. We are asked to calculate determinant of this matrix here. Yeah. And we got this matrix B is now just this DAE. So determinant of B that is asked, that is determinant of this Ci Cj inverse Aij, is nothing but determinant of this matrix DAE, but product splits over determinant. So what I get is it is determinant of D into determinant of A into determinant of E. But determinant of A remains as it is, and this determinant of D is diagonal matrix. So diagonal has entries C1, C2, Cn. So this is C1, C2 product Cn. And determinant of E contains all the inverses, C1 inverse, C2 inverse, Cn inverse. So let me just check. Yeah, yeah, C1 inverse, C2 inverse, and Cn inverse. So that is nothing but, so these are just numbers here. So I can club them and I get this C1, C1 inverse, C2, C2 inverse, so on, Cn, Cn inverse into determinant of A. That is nothing but determinant of, this is 1 into determinant of A, and determinant, and A is nothing but just this Aij. So that's what we are asked to prove. Okay, so yeah, we are done now. The first part of the proof, that is this is now done. Okay, now that this particular case, that determinant of Aij is determinant of -1 I plus j. So what we need to do here is the similar thing. What we need to do is, second, we have to see what my what we say. What my CIs will be for so in general we know determinant of Aij is determinant of Cj inverse determinant, oh sorry, Aij. We know this. In fact, we proved. So we have to choose what Cjs we need to choose in order to have this term to be equal to, so this to be equal to -1 power I plus j. And what can we do for that? We can just simply choose Ci's to be -1 power I. Okay, if we choose Ci to be -1 power I, or let me just choose some another. Uh, what? Yeah, not CI. Let me choose some other one. Yeah. Let us call it CT is equal to minus 1 power T. So then we know that then this CT inverse is also minus 1 power T. But I mean, that's what we know. Inverse of this will be the same thing, because since CT square will be CT into CT inverse, the inverse will be same thing, right? Because CT square is minus 1 power T square, that is minus 1 power 2T, and that will give me 1. Okay, so CT inverse is again minus 1 power T. So in that case, this determinant of Aij now becomes determinant of Ci, that is minus 1 power I. Ci is equal to minus 1 power I, and Cj is equal to again minus 1 power j. Okay, because Cj inverse will be again minus 1 power j because of this, which we, sorry, which we have. So minus 1 power j and Aij. And then this will give me determinant of minus 1 power I plus j, Aij. So for this particular case, what we had to do was to just assign this proper value or choose CIs properly. So that's it. That's what is asked in this question. There are many ways you can try to prove this or try to see this. But yeah, this is one way where what we did was we just tried to get hold of this matrix here using the information which we have. That is, we know what determinant of diagonal matrices look like, and how multiplying diagonal matrix, pre-multiply and post-multiplying by a diagonal matrix to given matrix, how the entries of a matrix change. So if you did not know, please know this, that it looks like this. So in general, I'm just writing this here. If D is equal to, in general, DA will be CIAIJ and AD will be CJAIJ. Okay, if you don't know, because this information, if it comes handy sometimes if you are trying to do some calculation or want, uh, and that's what is happening here, AE. When we are calculating AE, it is just multiplying the, where D is, where, let me check, where A is AIJ and D is, did something shift? Diagonal C1 to Cn. Okay, you can, if you did, sorry. Okay, this is something you can use, or if you did not know, you can also try and check this. Yeah, so that's what the first question was about. So let's move to next question. If you have any doubts, please raise those in the discussion forum. Yeah, so let's do the next question. Question 2. Check whether which of the following bases of Rn represents the standard orientation. Okay, so first one is n is equal to 2. v1 is equal to 1 comma 1 and v2 is equal to 1 comma minus 1. Second n is equal to 3, v1 is equal to minus 1 comma 0 comma 1 and v2 is equal to 0 comma minus 1 comma 1 and v3 is equal to 1 comma minus 1 comma 1 and third is n is equal to 4, v1 is 1 1 1 1, v2 is 1 2 1 1, v3 is 1 1 3 1 and v4 is 1 1 1 and 4. So this is what is asked to. So we have to find this, whether the given, whether which of the following bases of Rn represent the standard orientation. So let us recall the definitions as well. So, sorry. So, orientation in general, so for given vector space V, orientation is just base change matrix. So in orientation of Rn is, yeah. So orientation of Rn is an equivalence class of ordered basis. Okay, where when we have two bases, they are in the same class. So we say that they follow same orientation. So for example, in Rn, the standard basis, the basis EI of entries 1001, 010, E2 is equal to 01, 00, so on. It is considered as positively oriented uh, basis of Rn. Okay, so what in general to check the so orientation of Rn. So let me just write this. And orientation of Rn. In Rn, since we are in Rn, the determinant of basis change matrix will be a real number. So we either have it to be positive and it to be negative. And since it is basis change matrix, the determinant won't be negative 0. Okay, so determinant will either be positive or it will be negative. So based on that, we say that whether it represent the standard. So when we say standard orientation, it is orientation of standard basis. So yeah, so whatever the determinant the basis change matrix has, that orientation is assigned to that basis. So it will get clear once we do this. So orientation of Rn is an equivalence class of ordered basis. Okay, so ordered basis is important because once we do the order change, so when we talk about basis change matrix, even last lecture towards the end, I mentioned that when we talk about the basis change matrix or what we say, uh, linear transformation matrix of a given linear transformation, so it is highly ordered base. Okay, so the when we try to find the basis change matrix or a linear transformation matrix corresponding to particular basis, we the order is very important because we are literally entering how the coefficients of particular linear transformation, I mean, the matrix when we write, it is corresponding to, for example, this is corresponding to F1, F2, Fn, and each entry is corresponding to V1, V2, Vn, and so on. So what we are doing is, it is highly ordered oriented, okay? And when I'm writing this F1, I actually mean it that FU1, FU2, and FUN. So it is, I'm talking about linear transformation matrix of F from U to V and so on. So when I write here F1, the entry is a 1, 1. That is, what is the coefficient when I represent FU1 as a linear combination of V1 to Vn? So if I switch here V2 and V1, the entries will change, and that will change the determinant of matrix as well. We know that swapping two columns or two rows uh, gives the negative determinant of the original matrix. Okay, so this is what ordered basis means. So this ordered basis is important, where two bases B and B dash are in the same class, that is, have same orientation. If the change of basis matrix suppose we call it P from B to B dash has determinant of P or satisfies determinant of P positive. Okay, so they are either positively oriented or negatively oriented. It depends on what are. Okay, and as I said, swapping two bases. For example, if my B is V1 to Vn and my B dash is V2, V1 to Vn, sorry, V2, V1, V3, so on up to Vn, then you can see that the basis change matrix P here will be P, that is basis change matrix of V, B, P dash. It will be this, right? Corresponding to V1, it is 0. So what is happening is that V1 is 0 V2 plus 0 V plus 1 V1, 0 V3, and so on. V2 is 1 V1 plus, sorry, 1 V2, 0 V1, 0 V3, and so on. And rest are anyway, V3 is going to 0 something and 0 V3. So it becomes 0. So as I said, so understand that a basis change matrix is linear transformation matrix of identity matrix corresponding to given basis. That's what we are doing. So this is identity. So basis change matrix. If there are any doubts, please stop me and ask. A basis change matrix is a linear transformation matrix of, suppose I'm talking basis change matrix, basis change matrix of from B to B dash is a linear transformation matrix of identity transformation. Okay. That is, suppose if we are talking about V, so it is identity from V to V, and such that each X is going to X or V is going to V. Okay, and how that we are, I mean, corresponding to B dash. So this is what? This is V1, image of V1. So identity of V1, that is V1, but how V1 is represented in terms of basis B dash, right? We are going from B to B dash. So identity on V1 will be just V1, but how V1 is expressed in this ordered basis, where my basis is V2, V1, V3, and so on. Okay. So this is not, yeah, there are commas in between. This is set. Okay. And so this is 0, 1, 0. Second one becomes now V2 with, so this is identity. So just V2 as it is. So V2 is 1 V1, 0 V1, sorry, 1 V2, 0 V1, and so on. So 0, 1, 0, 0, and so on. And rest is as it is, right? Nothing is changing here. Rest is 0, except 1 here. and all the diagonal entries are 1 and rest is 0, as we know. And then determinant of P is -1 here because we are just swapping two rows. Rows or two columns does not matter. So determinant is -1. Okay, which is less than 0. So they are not from same orientation. Okay, they do not have the same orientation. That's what we are saying. So I hope you understood what this basis orientation means and what is standard orientation. So a standard orientation or so this is just definition of orientation, okay? And what is standard orientation is the standard orientation. So standard orientation when we talk about it is for RN, okay? Because we know the standard basis E1, E2, En. We do not have that luxury in case of any other random vector space. Okay, so this standard or positive orientation Rn is the equivalence class containing the standard basis E1 to En. Okay, so this is like we are setting a notation, sorry, that we will call a basis to have same orientation or positive orientation it if it has same orientation as this standard basis. Okay, so in general, basis V1 to Vn represents the standard orientation if the matrix A with columns. Okay, now we are in Rn. So we know how, we are in Rn. So all the vectors are rows or columns, whatever you want to look at them as. But we know it is a n tuple. Okay, so matrix with column V1 to Vn has determinant of A to be positive. Okay, if this determinant of A is less than 0, then it represents opposite or negative orientation. Okay, all these definitions are given in the exercise sheet itself. You can read those. So, and this when we are writing, I hope you understand what it means. Okay, it is basis change matrix from this standard basis. If I call this E, or let us call this B, and if I call this B dash, so this is from B to B dash, right? And or B dash to B. And so what I will do is B to B dash. Oh yeah, B to B dash. So what I will have, B is my standard basis, right? So B dash to B. Yeah, it is B dash to B. So my basis B dash is V1 to Vn. So V1 is some tuple, right? It will be some A1, A21, sorry, not 21, A11, A21, and so on, A2N1, N1, and so on. Okay, and V2 will be, again, since it is in Rn, right? V2 will be A221, sorry, A12, A22, and AN2 in Rn. So when I write V1 goes to V2, V1 and try to express it in identity in standard basis format, it will be A11 E1 plus A21 E2 plus A N1 En and so on. And now what we have to do is we just have to write the image of V1 under V1, but with respect to my original standard basis. So it will be just A11, that is this V1, A21, AN1, that is V1 in column format, right? And similarly, it will happen with everything. I think it will be, yeah, A12, A22, AN2, and so on. And Vn will be, so in general, Vi will be A1i, A2i, ANI. Okay, this will be in Rn. So everything will be of this form, A2n, ANN, and so on. And this is nothing but this matrix A that is formed with columns as matrix V1, V2, Vn. Okay, and that's what it says. So if determinant of this matrix A, this is my basis change matrix, right? And the orientation is defined by this determinant of this basis change matrix. So where is it? Where did I write that? Yeah, this is the main step, right? Determinant of P must be positive. So ultimately, this basis change matrix from B dash to B is nothing but this A, that is matrix with columns from this B dash, that is vectors V1 to Vn. That is my basis. And determinant of A will give me the orientation. So determinant of A will give me will give the orientation. I hope when I write this, what it means, okay? So that's what we will be doing here. So our question is to calculate and check whether this basis, whether it has standard orientation, whether it has positive orientation. So what we have to do is we will use this. We will just write those vectors as a column and check the determinant of that matrix. If it's positive, it belongs to the standard orientation. If it's negative, it does not belong to the standard orientation. So that's what we will be doing. So first one is n is equal to 2 and my v1 is 1 1 and v2 is 1 minus 1. Okay, so my A will be this matrix, right? 1 1 1 minus 1. And determinant of this will be minus 1 minus 1 minus 1. So that is minus 2. That is less than 0. Let me write this here, v1 and v2. Okay, and therefore this does not follow the standard orientation. Okay, so hence, therefore, this v1, v2 represents the opposite orientation or does not have the standard orientation. Okay, and see that here does not matter if we go from B to B dash or B dash to B. Okay, it won't change much because if we go from B dash to B, how it will be? It will be inverse of this matrix, right? But does not matter. Even if it's, yeah, if we go from B dash to B or B to B dash, the Linear transformation matrix will be inverse of this matrix. But does not matter what determinant is. All we have to know is whether it's positive or negative. So if I go from B to B dash, it will have some determinant. And if I go from B dash to B, it will have some determinant. But ultimately, those matrices are inverses of each other. So their product will be 1. So if B identity matrix from B dash to B s- suppose has negative determinant, the inverse, the this identity transformation matrix or the basis change matrix from B to B dash will be inverse of this number, and that will again have same uh, sign or same, what we say, parity, whether positive or negative. So what I'm saying in general, so let me just write what I'm saying is that I from if determinant of I B to B dash is, what I'm saying is I is from B to B dash, and I from B dash to B is, you can check this. In fact, if you don't know, uh, this B to B dash inverse, okay, and if, and we know that determinant of this product I from B to B dash and I B dash to B does not matter. No, no, yeah, that's it. That's it. Will be one, okay, because they are inverses of each other. So if this is negative, if this is negative, this has to be negative. So determinant of what I'm saying is I B B dash will be 1 by, or B dash B will be 1 by determinant of I B B dash. So if this is negative, this will also be negative, and okay, let me just, and if this is positive, then this will also be positive, okay. So going from B to B dash and B dash to B does not really matter. You can go from any basis to any basis and check whether they belong to same orientation class or not. Okay, so that's it. So second question was n is equal to 3, and we will be doing the same thing. It is minus 1, 0, 1. V2 is 0, minus 1, 1. And V3 is 1, minus 1, 1. And then determinant of A will be determinant of this matrix, right? Minus 1, 0, 1. We have to write it in as column. 0, minus 1, 1. 1, minus 1, 1. And we'll calculate the determinant using first row. So minus 1, minus 1, plus 1, plus 0, plus 1 into plus 1. That is, what is it? It is minus 1 into 0 plus 1. So that is just 1. Okay, so determinant of A is 1, that is positive, and hence, therefore, this determinant is 1, right? Yeah, it's 1. Yeah. So therefore, it has standard orientation. Therefore, the given basis has the standard orientation. Okay, if there are any doubts, please let me know. I hope you understood. Like, I'm just calculating determinant using first row, okay? Determinant using, okay. And next is similar, the 4 cross 4 matrix. It will be n is equal to 4, and my V1 is 1, 1, 1, 1. V2 is 1, 2, 1, 1. V3 is 1, 1, 3, 1. And V4 is 1, 1, 1, 4. And my A becomes now this. I'm explicitly writing A here because yeah, it is 1 1 1 1 2 1 1 1 1 3 1. And we have to calculate determinant of this one. But before we calculate, we would like to simplify this matrix because otherwise it will be too much. I mean, we can directly calculate determinant from here, but I won't prefer that. Um, so adding and adding two rows or adding multiple of particular row to another row does not change the determinant of matrix. Okay, so that's what we will do. What we will do is first R2 to R2 minus R1, R3 also R3 minus R1, R4 also R4 minus R1, and I will get this matrix, this new matrix A dash, and this will be 1 1 1 and 0 1 0 0, right? 0 0 2 0 and 0 0 0 3. Oh, so yeah, correct. Right, and now we can calculate it with respect to the first column maybe. So note that determinant of A is equal to determinant of A dash. Okay, so therefore determinant of A is determinant of A dash. Okay, please check this. If you don't know, check this. And that it is diagonal matrix first of all. So determinant will be just product of diagonal, that is 6. And that is definitely greater than 0. So therefore, hence this given basis has the standard orientation. Okay. So here it is asked with respect to standard orient. Yeah. So here we are asked whether given basis has standard orientation or not. So what we had to do was to just write the columns. So the given vectors as columns and we were through. But you might also be asked to check whether given two bases, whether they belong to same orientation class or not. So in that case, you have to actually calculate the basis change matrix and find its what we say, find its determinant and conclude whether the given bases are from same orientation class or not. Okay, and in that case, you can be smart enough to choose you want to go from B to B dash or B dash to B. Does not matter because we just saw from here that it won't matter which basis change matrix you choose from B to B dash or B dash to B. They will give you the same orientation. It does not matter, okay? And yeah, so we'll move to next question. Question 3, that let B be 3 comma 4 and W be 2 comma minus 3 belong to V, that is my R2. We have to compute the area of parallelogram QVW spanned by the vectors V and W. Okay, so this is our question. So what does this mean? That we have to, okay, we will just shift this here. So what does this mean when we say that a parallelogram spanned by these two vectors? So what it means is we have to see this. Okay. So this first vector v is 3, 4. So if I consider them this as my grid in R2, this is x-axis, this is y-axis. So 3, 4 will be somewhere here, right? So if I call this v 3, 4, and my another next vector is 2, -3. So 2, -3 will be here. So my parallelogram is this. It's from here. It's this. And then this again will be here. Okay, so this is my parallelogram. Okay. And we have to calculate area of this one. This is my W. It is 2, -3. So this is the parallelogram which we are asked to calculate the area of. Okay, and by there is direct formula to calculate, is just find the determinant of this. Just a second. Okay, so in general, this Q VW. So for in general, so this is this is easy to see and understand because we are in R2. Okay, but in general, if we are, so in general, so for in general, for V is equal to V1 comma V2 and W is equal to W1 comma W2. This Q VW is just all these elements SV plus TW such that 0 less than equal to S comma T less than equal to 1. Okay, in general it is this set. And when and it, we can see that this is actually collection of all these points here, this region. Okay, everything is between 0 to 1. So the scaling of this V is gone from 0 to 1 here. So 0 represents 0 comma 0 here. And when I ignore this section, let me just erase this and consider only if I ignore, yeah, if I ignore this TW and only look at SV. So my V is 2, 3, 4. So this is this span, right? So, and then I'm adding this TW to here. So for each this span, for 0, it will go till here, right? The point. For this point, I'm adding this element, this 2 3 here, from 0 again, from 0 to 1. So it goes from here to here. It will trace all these points from 0 to 1. So I hope you understand. So it covers all these point of this form. And similarly, if you want to look from W going to, so W is this, so 0 0, it is like this, and then I'm adding this SV to it. So SV is adding this point 3 4 to it. So it translate to here, and W2 comma 3 to here. And when I add each multiple, the addition goes like this, and it covers all this point in this parallelogram in R2. So in general, this can be done for any what we say, any vector space where we have inner product and so on. Okay, so and area via and the area of parallelogram is obtained by calculating the determinant. So let me just, for two vectors, v is equal to v1 v2 and w is equal to w1 comma w2 in R2, area of parallelogram, they span, is given by the absolute. The absolute means the modulus of that value. Okay, absolute value of the determinant of matrix whose rows, sorry, whose columns or rows does not matter, because determinant of A and A transpose is anyway same, so does not matter, or rows are the coordinates of V and W. That is again the matrix. That is the matrix. Since we are in R2, it is V1, V2 and W1, W2. You can write them as rows, does not matter, because anyway determinant of A and A transpose is same. So that is this matrix, and the area will be this V1 mod of this V1 W2 minus W1 V2. Okay, and yeah, that's it. So we have to find determinant of this given matrix, this two vector area of parallelogram covered by these two vectors V and W. So it is just determinant of matrix having these two as columns. So that is determinant of 3 4 2 minus 3, and that is minus 9 minus 8, that is minus 17. But I have to take modulus of this. So therefore determinant of, sorry, say for area of parallelogram, that is 17. QVW is 17. Okay. Is there any doubt? And does this minus just represent again? These are that it is in it. It does not belong to the orientation of standard basis. That's it. It is negative determinant here. That's what it represents, and nothing else. And similarly, again the same question about area of parallelogram. So let V be this 2 1 and W be 3 comma minus 1 belongs to V R2. And again we have to compute the area of parallelogram QVW spanned by this V and W. Okay, and again it will be determinant of absolute value of determinant of this matrix 3 minus 1 that is -2 minus -2 minus 3, and that will give me again -5. So that is 5. And so just this minus sign represents that it does not belong to, it does not have standard orientation. And determinant is 5. So yeah, and that's it. That's the area of parallelogram spanned by these two. And you can, I mean, it's not, it's this parallelogram, by the way. This 2, 1, that is, it is here. And 3 minus 1 will be here. So it will be this parallelogram. And we calculate that this has area 5. That's it. Okay, this was my 2, 1. And this is 3 minus 1. This is 0, 0. And this is what? 5, 0. And here this will be this addition of these two matrices. Sorry, these two vectors. So this will be here 5, comma 4 plus -3, that is 1. Okay, please understand this here. It will be good if you understand and visualize what this means here. And nothing. Yeah, so any doubts here what we did? Okay, so we'll move to the next question now. So next question is, mm, yes, let us do this one. Yeah. I think this is question 5. So let f1 to fn be functions on the set D with values in a field K. So that is K valued function. We have K valued function over D. And then this f1 to fn are linearly independent over K if and only if the function f from Dn to K such that this T1 to Tn going to determinant of this f1 T1, f1 T2, fn Tn, sorry, f1, f2 T1, go on, fn Tn, this is f2 T2, and so on. Okay, this is fn Tn. It is if determinant of on this Dn is not the zero function. Not the zero function means it's not identically zero function. Okay, so this function needs to be non-zero. That's what it says. This f here is non-zero. We are not talking about fn if fi is being non-zero. We are talking about this f which we defined here from dn to k will be it is not the zero function. Okay, so the zero function. So zero function is function where everything is mapped to zero. Okay, so they are saying that this f1 to fi's f1 to fn are linearly independent over k. So this f1 to fn being linearly independent over k means there is no linear combination of f1 to f1 in K that will give me 0. That is, no linear combination of this F1 to Fk will give me a 0, what we say, zero function. I hope you remember this, that this F1 to Fn being linearly independent means there does not exist any A1 to An in K such that this will happen, that A1 F1 plus An Fn will be 0. Okay, this 0 here is zero function. Okay, that is for any element from D, the function is mapped, the function takes value 0. Okay, so yeah, so we have to prove this. It is if and only if statement. So we have to prove both the sides. So let us start with the proof. So first, that suppose first side, if f1 to fn are linearly independent, then f is not the zero function. It's not saying that f does not take 0 as a value. Okay, it is saying it's not the zero function. So even at some, for at least for some t1 to tn, if I can obtain this, I'm okay. Okay, please understand this, that this is, let me write this. This is the zero function, that is, everything is mapped to 0. Okay, and it is saying it not the zero function means, oh, let me write, not the zero function here means at least at some t1 to tn in dn we have f of this t1 to tn non-zero. That's what it means for this function to be not the zero function. Okay, there are two different things. Non-zero function means it does not take 0. I mean, yeah, not the zero function means at least at one point it has to be non-zero. Okay, uh yeah, so let us start with we are already given, so we are given that f1 to fn are linearly independent. We have to show that there exists, as I said, there exists at least t1 to tn in dn such that f of t1 to tn, that is determinant of this matrix again. Let me just write shorthand. Fitj is non-zero, okay? This Fitj is this matrix. That's what we have. So we have to find this T1 to Tn. So suppose this T1 to Yeah, suppose for all T1 to Tn in Dn, this f of T1 to Tn is 0. Okay, we'll do the proof by contradiction. So I'm taking that, suppose for every such tuple T1 to Tn, I get that f of T1 to Tn is 0. That is determinant of this Fij, this matrix here, is 0. Okay, so this means for every choice of T1 to Tn in Dn, no, in D, the matrix A T1 to Tn has linearly dependent. Since the matrix, since we are talking about this 0, so matrix, this matrix A T1 to Tn is this matrix. I'm just giving the name A T1 to Tn. It is just this matrix F2 T1, yeah, F and Tn. So F1 T2, yeah. This the original matrix which we had, F1 Tn, and this F and Tn. Okay, this matrix which I just wrote here, A, has linearly dependent, okay? Dependent, this implies, okay? Right, because the matrix itself, so determinant is getting 0. So this matrix which is formed, it will have determinant 0. So at least two of the columns, I mean, the columns becomes linearly independent, linearly dependent, because if it were linearly independent, I will get non-zero determinant. Okay, so they are linearly dependent columns. So that is the columns, that is the columns of A are this F1 T1, right? F2 T2, F and Tn, call F1 T2, F2 T2, and F and Tn, F1. And this is the final column, F1 Tn, F2 Tn, and Fn Tn. Okay, these, that is, these columns are linearly dependent. Columns of A are linearly dependent. And this is true for every such choice of T1 to Tn, right? So if these columns are linearly dependent for all, so if these columns are linearly dependent for all this T1 to Tn, then for each T1 to Tn. There exists some A1 to An in K such that since these columns are getting linearly dependent, I will have this linear combination, right? This F1 T1, F2 T2, Fn Tn, sorry, F2 T1, Fn Tn plus A2 F1 T2, F2 T2 and Fn T2 plus An F1 Tn, F2 Tn and Fn Tn. This whole becomes 0, 0, right? It will give me 0 column because they are linearly dependent. So this gives this A1 Fi, yeah, A1 Fi T1 plus An Fi Tn is equal to 0, right? For each column. So I am not, so what I'm doing is I'm multiplying each entry here and then looking at the first row, it is giving me A1 F1, A, uh, A1 F1 T1, A1 A2 F1 T2, An Fn Tn, A1 F1 Tn to be 0, right? And second column will be A1 F2 T1 plus A2 F2 T2 plus An F2 Tn is equal to 0. And final column will be A1 Fn T1. So A1 Fn T1 plus A2 Fn T2 plus An Fn Tn and so on. This is T2. So this becomes system of equations like this for all I from 1 to n. There are n equation each for each row. And with all non-zeros, with not all AIs are non-zero. Okay, it depends on depending on T1 to Tn because we are obtaining this for each Ti I'm getting linearly independent columns, right? So as Ti changes, this linearly dependent column. So this linear dependence changes because the matrix changes with each change in Ti. I mean, with each change in tuple T1 to Tn. So now consider this function. So consider this function g from D to K defined by g of t as a1 f1t, a2 f2t, and so on an fnt. Okay, now this is entirely different function. Okay, this g is now function defined like this. Where this a1 to an are chosen. Yeah, for some t1 to tn such that not all are 0. And we can do this because these FIs are given to be linearly independent. Okay. And so we now evaluate this this G at T is equal to Tj. Then I get G of Tj is equal to A1 F1 Tj plus A2 F2 Tj plus so on An Fn Tj. And this will give me 0, right? For all j from 1 to n. Because that's what these A1 to AIs are chosen. So this A1 for this T1 to Tn, these A1 to AIs are chosen such that I'm getting linearly dependent columns. So when I evaluate this G at this chosen A1 to AIs, since each of this column was becoming 0 for this A1 to AIs, this function will take value 0 for this T1 to Tj. I hope you understand this. So this G is essentially becoming a column of this rows of this linear combination. Okay, so that's what my G is, and we know that it is equal to 0 for chosen A1 to AI. Okay, so this has become 0. So if we choose now, so if we can choose, so suppose that D has now n points, okay? So if we choose this T1 to Tn in D, and if determinant of this Fi Tj is 0 for all this T1 to Tn in D, then the columns are linearly dependent always. Then the columns of A are linearly dependent always. And but the linear independence of F1 to Fn implies that this map P from Kn to Kd defined by this, right? A1 to An to A1 F1 plus An Fn. Okay, so this is just map, okay? Is injective. This is because of the linear independence of F1 to Fn. If that's not the case, then it will contradict the linear independence, right? Because what is determinant of this Kn? It is determinant of, dimension of Kn. It is dimension of D plus, image space plus, the rank nullity theorem I'm trying to prove here. Rank of image plus rank of, so what I'm saying is, so N will be dimension of image plus dimension of kernel, right? But dimension of image, since F1 to Fi's are linearly independent, it will be N. So this kernel has to be, dimension of kernel has to be 0. dimension of Kn, that is n. And then this becomes 0 by rank nullity theorem, okay? Since F1 to Fn are linearly independent. Okay, so this, and hence what we, but since we have this T1 to Tn, since, but we can choose T1 to Tn in D such that this A1 to An going to GT1 to GTN. Now this new map from Kn to Kn. Wait, what we are doing? Evaluating at T1 to An the matrix represents the linear map. Okay. So evaluating this at points T1 to Tn, which we chose already here, we get a map. Yes, we get the matrix AT1 to Tn represents the map Kn to Kn given by A1 to An going to GT1 to GTN, right? That's what we are doing. So T1 to Tns are from D, and then what we are doing is we are taking this A1 to An and then evaluating. So this column will be, A matrix will be what? It will be, yes, it will be just F1. I mean, we know what this G is, right? It is this A1, this A1, F1, TJ, and so on. So when I go from A1 to An, it essentially gives me, and I evaluate this phi at this A1 to An, it gives me this, right? A1, F1, T1, A2, F2, T2, and so on in first column, in first entry. And the last entry will be this A1, F1, Tn, and so on. So this is now new map from A1, An to G1, from this A1, A2, An map to this GT1, T2, Tn. And this map now has non-zero kernel, because we have this A1 to AIs chosen such that it becomes 0, right? This A these AIs are chosen such that this map is actually becoming 0 for this T1 to Tj. So this new map Kn to Kn has non-zero kernel. And determinant of this, so this matrix now, this new map, let me call this psi. This map psi has non-zero kernel due to choice, as we can choose, if I call this star, AIs which can give G of Ti to be 0 for all 1 to, for I from 1 to n, as we did for star. right? And so the determinant, if 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 the representation matrix, if the matrix of psi has determinant 0 for all t1 to tn, it is vectors f1 tj, fn tj allows a non-trivial linear combination of f1 to fn, and this will give me 0. Okay, f1 to fn allow the non-trivial linear combination. So we we got this new map psi, and this psi has a non-zero kernel, so we can choose this a1 to ai to be non-zero, and this a1 to ai getting non-zero will give me a non-zero non-trivial linear combination. Since this has non-zero kernel, it means there will be some non-zero tuple of a1 to ai's such that this becoming 0. So I can choose this a1 to ai will give me the exact a1 to ai where with coefficients for f1 to fn, which will map to 0. So the columns of this matrix A, this matrix here, will have non-trivial linear combination, which is mapping to 0. And that will then give me that this f1 to fi have non-zero linear combination, which is mapping to 0. And that will give me that they are non-trivial, okay? So, so there must be, hence, but f1 to fn uh, are linearly independent. This contradicts the linear independence of f1 to fn. So understand that we define two maps here. This phi will have non-zero kernel, but then we are defining this new map, evaluation map, and this has non-zero kernel, and that gives me the contradiction for linear independence of f1 to fn. So, but f1 to fn are linearly independent. There must exist some t1 to tn such that this f1 pj fn tj for j from 1 to n are linearly independent. And this now becomes this choice of t1 to tn which we have will give uh, will give me the non-zero value of that determinant, okay? For j from 1 to n are linearly independent, and then that is what that is determinant of fi tj, right? Will be non-zero. Okay, so what we did here, I hope you understood. So what we had is we defined this G here. Then we chose these n elements from D. Then this determinant of Fij, suppose it is 0. Okay, then, and it is 0 for any given choice. Then we have this columns of 8 to be linearly dependent. Then this map P from Kn to Dn, we don't care whether it has non-zero kernel or not. But what we do is, yeah, I mean, it has non-zero kernel. So what we can do is we can choose this T1 to Tn. And then we define this map T1 to Tn such that psi from Kn to Kn, that is evaluation. Okay, A1 to An going to G T1 to Tn. G has coefficients as An. So I hope you understand how this map here is defined. And if this map has and this map has non-zero kernel, and then if this and this map has non-zero kernel implies we have a linear combination of A1 to An here. That is when I evaluate at each Ti becoming 0. And if I get that, then, and if this is happening for each T1 to Tn, then I will get a non-zero linear combination of these columns F1 T1 Tj to Fn Tj, this one. And that will contradict the linear independence of F1 to Fn because this is happening for each T1 to Tn. And but that's contradiction. So there must exist this T1 to Tn such that these columns must be non-zero. And once we have these n columns, which is non-zero, then that is my matrix A. That is F1, T1, F2, T2, and Fn, Tn. This matrix now becomes non-zero because each of this is linearly independent vectors now. I hope this is okay. I mean, yeah, even this is not that trivial. But yes, we can arrive at. So it is just ultimately we have to find these vectors T1 to Tn such that there the determinant is non-zero. Okay, that's what our aim was, that there exists some T1 to Tn for which this determinant is non-zero. And we obtain this. This T1 to Tn could be same, different, we don't care. It is just some elements from D such that I want when I these columns to be linearly independent when I look at them. Where is it? Yeah, these columns I want to be linearly independent. So I want to just find such T1 to Tn. And for that, we defined this map and this map here, psi from Kn to Kn, this evaluation map. And this G, this A1 to An changes with this G. And if this map has non-zero kernel, then we are getting problem with, then we have problem with the linear independence of F1 to Ft, which is given. Okay. Now the converse is left. So if given the so now the converse statement is if f is not the zero function, then f1 to fn is are linearly independent. Okay, so assume this there exists t1 to tn in Dn such that f of t1 to tn is equal to determinant. Since f is not the zero function, so there exists some t1 to tn in Dn, right? It is not the zero function. So such that this Fij is non-zero. I can choose this because f is given to be not the zero function. So then the matrix, this A again of this F1, T1, F2, T1, Fn, Tn, and this F1, T2, F2, T2, this, sorry, Fn, T2, and so on, F1, Tn, F2, Tn, and Fn, Tn, has determinant non-zero, right? That's what this these two are equal, these two matrices. So its column must be linearly independent. Hence, the columns of A are linearly independent, right? And then suppose F1 to Fn are linearly dependent, then there exists A1 to An in K such that this will become zero, right? A1 F1T plus An Fn T will be zero for all T in D, right? Then if we evaluate, so if we evaluate T at Tj, then this A1 F1 Tj plus A2 F2 Tj plus An Fn Tj will be zero for all. One from J to N. So that is, and if I try to write it in the matrix form, everything is getting, so A1 is getting multiplied to column. So we know for column multiplication, we have to post multiply the diagonal. So this becomes this A matrix into A1, A2, An is becoming zero now, right? A was just Fitj, and now what is first column of Fitj? F1 T1, F1 T2, F1 Tn, right? So the first column becomes, right? Yeah. I think we have to pre-multiply. Does not matter. Where, let me write, where jth column of A is J's F1 Tj, F2 Tj. Yeah, F and Tj, as we know. Transpose. So since determinant of A is non-zero and A is invertible because determinant is non-zero, this implies that yeah, this is getting multiplied to each column. Each AI is getting multiplied to each column of A. And this implies that only possible solution A1 to An must be zero, right? Because the given determinant is non-zero. And if I get something like this, it means the linear combination of columns is getting zero. But then the determinant will be zero. But that contradicts the given condition. Okay, so this contradicts the assumption that A1 to AN are all non-zero. Okay, so hence F1 to Fn are linearly independent. Okay. Here, this not all zero. Okay, so we started with linear combination and then we arrived at condition where it was contradicting the determinant of A as non-zero. Okay, understand that when we say the determinant of A is non-zero, both rows and columns are linearly independent. So does not matter we check it for columns or row. If this A1 to AI get multiplied to column or multiplied to row does not matter. Both of them must be linearly independent. I mean, both the rows and both the set of rows and both the set of columns. So ultimately, what we were getting is that some linear combination of rows or the columns of A was becoming zero. That would give me that this determinant of A is zero. But that's not the condition. This F given is non-zero function and hence the determinant of A has to be non-zero for some T1 to Ti's. And yes, so that's how we got the contradiction. Both, I hope this is clear. Any doubt? We'll do this one. Yes. And then we, yes, this one. Just try to do this. We'll see how much. I think this was question, I don't remember, maybe 6 or 7. So let A be Aij belongs to MNR, be n cross n matrix over real numbers. And suppose that each I from 1 to n have this mod of Aij is greater than summation j from 1 to n with j not equal to I, summation Aij mod of Aij. So this Aijth entry is greater than the summation of rest of the entries. Also not Aij, it's Aii. See, so the diagonal entry in particular column is greater than addition of rest of the, strictly greater than addition of rest of the entries in that row. That is the given condition. And then what they are saying is this A11 up to ANN, a determinant of A is greater than 0. We have to prove this. So what they are saying is They're directly not saying that determinant of A will be 0. What they are saying is determinant of A multiplied by this A1 to AN is 0, is greater than 0. So for example, if I have something like this, 2, 1 and 4, oh, in fact, -1 we can take. It does not matter. Modulus they are saying, right? And we can take -4 or just take 4. We'll check this statement. I'm just trying to check this statement. 2 must be greater than equal to modulus. So suppose take 3. Okay. And what they are saying is determinant of this A1 AN into determinant of A must be greater than 0. So A1 AN is -2, 4, and determinant of A is -8, -3. So that is 11, right? This is anyway, okay. -11. So this is anyway greater than 0, right? This is non-zero and now non-negative gate plus. And understand that if I add -4 here, the determinant, it becomes -4. This condition still remains the same because it's modulus, right? So adding negative to anything won't change much. So this becomes 8 minus 3, that is 5, and still greater than 0. And here again, if I add minus to this section here, so it becomes 4 here, 2, 4. So it becomes, the determinant is minus now, minus something. This is -8 plus 3, so this is -5. And determinant still remains positive. So this here is pretty strong statement. We do not know whether AII is actually greater than the given number. It could very well be negative. For example, in this case here, for something like this. But still the statement holds. Okay, we checked. So that's what this statement means. And we are trying to now prove this. Let us try to prove. So first thing is we will check that determinant of A is non-zero because we have to check this is greater than 0, right? So, and see, there are two things here. This here is a strict inequality. Something is modulus of something is strictly greater than this thing. So this AII must be non-zero, right? Because if AII is 0, this is modulus of something, even if this summation, and this everything is non-zero. And this has to be strictly greater than this AII must, modulus of AII must be strictly greater than this number. So even if this adds up to 0, for this to be strictly greater than this number here, this has to be something positive. Okay. This will be at most 0. Okay. This will be at least. So this is less than equal to 0, right? Sorry. This is greater than equal to 0, this term here. And I want this to be strictly greater than this greater than equal to 0 term. So this has to be strictly greater than 0. Okay. So this AII must be non-zero always. So this entire thing, to assure that this thing, so we have to prove that this is strictly positive. This thing, this number here is positive number. So this condition, this given condition here takes care that this portion here is non-negative, or sorry, it's non-zero. This portion here is non-zero from this given condition directly. So now we have to check whether this determinant of A is non-zero or not. Then we will talk about it being positive, okay? First, our aim is to check that this number here remains non-zero. Then we will look at whether it's positive or negative. So, yeah, so we will first check whether determinant of A is non-zero or not. So, to check whether determinant of A is non-zero. So a matrix A is invertible if determinant of A is non-zero, right? So which is equivalent to saying that the linear transformation x going to Ax has trivial has no non-trivial kernel, that is has trivial kernel, right? Because when we do this x, so this is from Rn to Rn, okay? Has trivial kernel. Because otherwise, this will be again linear combination of A that would, if this has non-zero kernel, this means again the columns are mapping giving zero linear combination, and that will again give me the determinant of A is zero. And we don't want that. I hope my handwriting is still readable. I'll try to write better. So suppose there exists a non-zero vector x from x1 to xn in Rn such that Ax is equal to 0. Okay, so the ith component of Ax will be, so this is the condition for invertibility or determinant being non-zero means. So now I have to show that this determinant of A is non-zero. So what I'm doing is I'm again assuming that suppose it is not the case. Okay, and suppose that there exists a non-zero vector. So see, what I'm saying is that we have to prove this, but it means this, and it means that there exists no this linear transformation has trivial kernel. So to prove this, I'm assuming that suppose it has non-trivial kernel. This linear transformation has non-trivial kernel. Okay, so this gives AI1x1 plus AI2x2 plus AINXN to be 0. That's my call ith row, okay, of matrix AX. Sorry, not. This is column AX, and each entry is this. Each ith component of this AX is this. Okay, and since X is a non-zero, choose index I such that mod xi is maximized. Okay. So this x is x1 to xn. So I choose the I such that maximum of this. So this is I is equal to j such that xj is equal to max of xi, I from 1 to n. I hope you understand this, what I wrote here. Okay, so this is I'm taking maximum of xi's and xj's maximum of xi, and whatever this j is, I'm assigning that I here. Okay, and maximum exists. We are in finite set. Uh, yeah. So that is this. That this mod xi is maximum of j mod xj. That's what I wrote here. And positive. The modulus. I'm looking at the modulus. Okay. So for this I, this aii xi, this is aii xi is minus summation j not equal to I aij xi xj, right? I'm just taking this and everything to the left hand side of this equation. So this is from here, I'm going to here. And then take the absolute values. This implies that mod of aii mod xi is equal to mod of summation j not equal to I aij xj, right? And this will be less than equal to this summation, right? This I hope you all know. And since x j is less than equal to xi for all j, I will get that this summation mod aij mod xj will be less than equal to summation j not equal to I mod aij xi, and I'm just taking this mod xi common. So this is j here. So now I'm evaluating this quantity here. Okay, this is this, and for each xj this is greater less than equal to xi. So this becomes summation j not equal to I mod aij. So from here, so thus we get this mod aii mod a xi is less than equal to mod xi summation j not equal to I mod aij. Okay, and since this mod xi will be positive, right? Because x we chose to be non-zero vector. X was non-zero vector. So this mod xi will be strictly positive. We can just multiply by its inverse and it won't change the sign. Okay, it won't change. Since it is positive, just removing this won't change the sign. So I get aii less than equal to summation j not equal to I mod aij. But this contradicts, right? This contradicts the given condition that mod of aii is strictly less strictly given condition is that this thing is strictly greater than. Okay, so therefore hence no such xi exists. Hence no such x exists. Okay, x is equal to this x1 to xn exist. Okay, because if such non-zero x exists, this would be positive and we arrive at the contradiction. So no such x exists, and hence this ax no non-trivial has no non-trivial kernel, and hence determinant of A is non-zero. Is this okay? And therefore A is invertible. So we now have the information about A being invertible at least. And now we have to just check for the sign, like how the sign of this A1 to AN and so on will change the determinant of A. It will take some time, but it's not that trivial. So the idea is we ultimately define the diagonal matrix using these AIs. I mean, we use this. We define some, use some diagonal dominance. This is how to explain this. We use some complex analysis to arrive at the conclusion. We define the complex numbers. We choose some disk of complex number with this condition. Let me just write this something like this. We define this disk at Z in C such that mod of Z minus AI less than equal to summation J not equal to I n mod Aij. And we show that this one has no origin. You can try doing this, okay? Uh, it will take some time. We have one session tomorrow, so maybe we can try to discuss this in detail tomorrow. But for now, understand that the disk are defined there. Uh, this we try to find elements in those disks with such that this AII becomes greater than zero and less than zero with some uh, coefficient, and ultimately we get the determinant of matrix A to be product of this. We arrive at eigenvalues, and the determinant of A becomes eigenvalue with positive AII, negative AII, and the determinant of these entries. And ultimately we get that this determinant becomes positive because the number of this negative eigenvalue and positive eigenvalues, they sort out somehow. So for now, I hope this much is okay. You can check this, or we can check that A11 ANN determinant of A is greater than 0. You can check this on your own if possible. Otherwise, we will discuss this in next class because we are already out of time and this will take some time. So we will do this in tomorrow's class maybe. Tomorrow we have again one tutorial session from 6 to 8. So let us meet there. So for now, at least to understand the determinant of A is invertible, A is invertible was okay to understand. If there are any doubts in at least knowing that determinant, this A is invertible, please let me know. Otherwise, yeah, we'll do this one tomorrow. And yeah, so that's it. We'll meet tomorrow. Oh, thank you. If there are doubts, please let me know. Otherwise, we can end the session and we'll do this tomorrow. Yeah. Okay. Okay. Thank you.